Hello, welcome to Electrochemistry Part 2. In this video I want to show you the concept, or I suppose it would be some bit of a review of the idea of half reactions. So a half reaction is where you split up a chemical reaction into its oxidation and reduction parts. So when we're talking about oxidation and reduction, we're talking about reduction, the gain of electrons, and oxidation, the losing of electrons. So with any chemical reaction, there's always an exchange of electrons one way or another. And so this oxidation and reduction can be found within chemical reactions. It's very important, of course, in electrochemistry, because when you're looking at how does a chemical change transfer into an electrical one, well, if you can take this oxidation and reduction, this is a flow of electrons. If you could flow this through some kind of a wire or some kind of a thing like that, well, then you have electric current, and that's what we do. So we do with batteries and such like that. So we're going to learn about that with our cells, our voltaic cells in the following videos. But in this one, we're just going to look at half reaction. So here's our reaction. We have iron combining with hydrochloric acid, and so it's going to create hydrogen gas and iron chloride. It's going to bubble away. It's going to disappear for the most part. So what we're going to do then is we're going to look at this in terms of oxidation and reduction. So the oxidation half reaction shows electrons as products right here. Because what's oxidation? Well, oxidation is the process of losing electrons. So you have them here. On the other side, they're separated from you. So oxidation is going to show the reactant side, it has its electrons, and the product side, it's going to show them released from it. Reduction would be the opposite. And so in reduction, you're gaining electrons. And so on the reactant side is where you put the electrons. I'm going to put my negative in there. All right, so here's the reaction. The first thing, and the most important thing to do, going back to the first video, is to assign oxidation numbers. So elemental states are 0. So iron here is 0. We know that hydrogen is +1, and that's going to make this one -1. Okay, so this one is a +2 on this side. Why? Because this is a -1 here still. And so we have two -1s, making this one now a +2. And so what happened? Well, the iron obviously lost 2 electrons. You see, the iron went from a charge of 0 to +2, meaning 2 negative charge were removed from it. So here's what we see. We see iron going to this. All right. We also see a change with hydrogen. So in this case, hydrogen is +1. And over here, it goes to its elemental state, which is 0. So going from +1 to 0 means an electron was added. So we'd say that iron was oxidized and hydrogen was reduced. All right, so what do you do with this information? Well, there's one thing that you can do that is really, really useful, and that is this process of, let's get rid of this, this process of taking a look at these half reactions and analyzing them. So, for example, when you're looking at a half reaction, you can check out the chart in the back of the book, which is called a reduction potential chart. So the reduction potential chart only shows the ions being reduced. You see, they're all in this case. You see the electrons all as reactants. Well, so what we can do though is that also tells us what the oxidation is. So lithium plus an electron is going to go to solid lithium, right? And it's going to be a -3.50 volts. So the opposite of that, which is the oxidation of that, if we just take this and we flip it, so just turn the arrow back the other way, so solid lithium going to ionic lithium and losing an electron is going to be a +3 volts. Now, one of the things that you're probably commonly aware of is that we use lithium ions for all of our batteries. And why is that? Well, look at these reduction potentials. Lithium is by far the highest. And so here's the opposite of lithium right here. Lithium losing that electron, being oxidized, is positive 3 volts. So very small atom, very small ion, and has a tremendous yield. And then also what we find is the higher the potential, the higher the reduction potential, the more likely it is to be spontaneous. So this particular thing is going to occur on its own, lithium turning, and you could actually gauge these like this, and you could say potassium, would be next. And as we go down, it changes. In fact, some of these flip entirely the other way, where their charge goes the opposite direction. So actually, the reduction gives you more charge than their oxidation. So so what we do is we'll couple one with a positive reduction charge and a negative oxidation and a negative reduction charge, and then they'll flow into each other, and that's how we make batteries. Another thing that we can do is we can use the reduction potentials and the half reactions to figure out the total charge of an entire reaction. So if we're going to look at this reaction right here, let's look at zinc combining with silver. So zinc combining with silver turns into the zinc ion, and the silver ion turns back into the solid form. So we have two half reactions. We have zinc, which is over here is losing an electron, right? So zinc is oxidized. So here's the oxidation half reaction. Zinc turning into the zinc ion plus 2 electrons. And then we can look at that up here. So if we find the zinc, where is my zinc? There it is right there. We find that the zinc, and this of course remember only shows it in terms of reduction, so we flip it the other way, turn this arrow back the other way and turn the sign to positive. So you can see I've done that right here. So this has become zinc turning into these, become positive 76.76, and so then we can also look at the silver, right? So the silver gains an electron in this, you might say, well, hey, there's 2 right here, so shouldn't we carry that down to here? Well, actually, no, you don't. When you're actually figuring out these overall reduction potentials of an entire reaction, you don't factor in the coefficients from the balanced equation. You just leave them right so. So just keep that in mind, because notice I did not put the 2 right here, and that was on purpose. All right, so the reduction of silver, if we look that up, here it is. Reduction of silver is plus 80, and that is, of course, these are all reductions. And so we can add those together, and so our total voltage for this exchange is going to be 1.56 volts. So if we put these two together, one's going to flow to the other, and see, that's exactly what I was talking about. You couple one with a negative reduction and a positive reduction, and they're going to flow into each other when you turn, because one's going to want to oxidize then because it's negative, and the other one's going to want to reduce because that's positive. So yeah, and so then that creates a flow of electrons, which gives us a voltage. So this is how you would solve for voltage problems using reduction potential table. This table is also provided for you on the AP exam.